Now section 2, we're talking about uniform motion, and we saw uniform motion in the last chapter. We talked about it a little bit. That means we have constant speed, basically, okay? Anytime we have uniform something, it just means something is constant. So in this case, uniform motion, we have constant speed, and we're doing it in one dimension, so that means we have straight line motion, since we're doing it in one dimension. Straight line motion, in which equal displacement occurs during any successive equal time intervals. If we have equal displacement in equal time, that just means we have constant velocity. Okay? So anytime you see uniform motion, it just means constant velocity. What would the position versus time graph look like for uniform motion? So if I draw, let me put a little sketch on here. What is a position versus time graph going to look like? For uniform motion, do you think? Linear. Yeah, some kind of linear situation. Something like that. Exactly. An object's velocity, so v sub x if we're moving in the x direction, is just the slope of the position versus time graph. We've talked about that already. So v sub x will be the rise over run on that graph, or delta x over delta t, x sub f minus x sub I over t sub f minus t sub I. All of those things we've already seen. The position equation then for an object in uniform motion. In uniform motion, remember the velocity in the x direction is constant if we're moving in the x direction. If we're moving in the y direction, it's the same idea. It's just that we'd be using v sub y. We have our first uniform motion equation. X sub f equals x sub I plus v sub x delta t. So that's a position equation. Now in terms of the displacement, we'd have delta x is the displacement, and we have v sub x delta t. So now we have a displacement equation and a position equation. X sub f is the final position, x sub I is the initial position, v sub x is the velocity, of course, and then delta t is the change in time. And that takes care of all of the little unknowns for both of those equations. So pretty straightforward. Now, how does this correlate to what we know from like an algebra class? So in algebra, we know that this is a linear situation. Y equals mx plus b. Y would be the y coordinate, or that would be our like final position, equals the initial position would be like the y-intercept here, and then look right here, the m and the x, we have the velocity is the rate of change, and the delta t is the x right here. How much are we allowing this thing to go on? So there is a direct correlation in this equation right here that we're talking about in physics to this equation right here that we learned back in Algebra 1, okay? It's just that you're using different letters that represent the things that are going on in physics compared to the usual numbers that we dealt with back in Algebra 1, okay? And it's just a matter of switching your brain over to what we're talking about here, all right? These are not meant to confuse you. They're meant to actually help you understand how the correlation is occurring. Okay? All right, so these formulas here are not actually new. They're just using letters instead of what you're used to from algebra. All right? But you have to know them and be ready to use them. So, proportional relationships. So we say that y is proportional to x if they are related by the equation in this form. And again, this is Algebra 1 stuff. So in Algebra 1, we said y equals kx. Or after we said that, then we said y equals mx. And then we found out that those graphs go through the origin if we were to graph them. They're linear relationships that go through the origin if we graph them, okay? Here we're saying y equals cx. It's all the same thing, all right? So c is the proportionality constant. K in Algebra 1 was the proportionality constant. It's all the same thing. All right, m is the slope, and it's the proportionality constant. It's all the same. All right, so a graph of this type of equation is linear and passes through the origin still. In this type of relationship, if either x or y is changed by some factor, then the other variable is changed by the same factor. And that's what a proportional relationship is all about. If I change x by 3, then y changes by 3. If I change x by 1/3, then y changes by 1/3. Okay, and that's what I'm saying here. Doubling x means doubling y. Decreasing x by a factor of 3 decreases y by a factor of 3. If two variables have a proportional relationship, then we can draw conclusions from ratios without actually knowing the proportionality constant c. And this is known as ratio reasoning. And we do this quite a bit. You do it actually all the time without even thinking about the fact that you're doing algebra in your head. And people just kind of have an inherent knowledge of this, and they don't realize that they're doing this, and they're like, oh, I never use algebra ever, and actually you do. So anyway, let's see. A train is moving due east at a constant speed. A passenger notes that it takes 10 minutes to travel 12 kilometers. How long will it take the train to travel 60 kilometers, do you think?
Oh, so that's 5, so 50 minutes.
See how fast you did that?
Yeah.
You realize that there was a proportionality situation here. These two things here had that relationship to them. Now, I could sit here and do this in an algebraic way. In fact, it's 10 minutes over 12 kilometers. It took us 10 minutes to go 12 kilometers, so I set up a proportion. How long will it take is something I don't know, so I put x there to travel 60 kilometers. Like if I was in Algebra 1, teaching this to my Algebra 1 students, this is what I would do, right? But people just have an inherent knowledge of this already. We don't need to know the proportionality constant to figure this out. You can just do it, right? So to solve this, you would say, well, I went 10 minutes to travel 12 kilometers. I understand that it's 5 times longer, so it'll take me 5 times longer, right? So 5 times longer than 10 minutes is 50 minutes. There's my answer. That's ratio reasoning. Pretty straightforward. Okay? I don't need to do the cross multiplying and all that. Okay? So, finding the position from velocity graphically. All right, so suppose a car moves east at a constant 12 meters per second for 2 seconds. How far did it travel in that time?
24 meters.
All right, so we already know the answer, 24 meters, right? That's obvious. But now draw a velocity versus time graph. Okay, so velocity versus time graph. So let's write that answer down first. 24 meters, that was easy. Okay, now velocity versus time graph. So I draw axes, and I know my time is going to be in, what are my units?
Seconds.
Seconds, thanks. And then over here, velocity is
12 meters.
meters per second. Okay, so now, we went at a constant 12 meters per second, so I'll just put 12 meters per second right here, 12. And we did that for 2 seconds, so I'll put 2 seconds right here. That looks good. Okay, now what does 12 meters per second, a constant speed of 12 meters per second look like on my graph? How do I draw that?
Straight.
Yep, horizontal is what you meant, right?
Yeah.
Okay, good.
Yeah, straight.
Okay, so now what is the area under the curve is the question. So this is in quotes, area under the curve. It could be a curved situation. Right now we just have a horizontal line. It's still considered a curve mathematically, okay? What is the area under the curve? Is asking me if I were to draw like that down, now I have a geometric shape. What is that geometric shape?
Rectangle.
It would be a rectangle. So what's the area of the rectangle? Well, this here would be the base, right? And what is that length?
Base times 2.
2. And what is this length here?
12.
And the base times the height would be 24 square units, right? But we know what the units are. This is units of seconds, and this is units of meters per second, right? So this would be 24 meters per second times seconds. So now we just got to figure out what meters per second times seconds is.
24 meters times s squared.
If I write this a little bit better, meters per second times seconds, what happens?
Meters over S squared.
No, that seconds is on the top and the other seconds is on the bottom.
MS over S.
What happens?
24 meters. It cancels out.
Meters
Yes.
per second per second.
The seconds on top and the seconds on the bottom divide out, and I'm left with just meters. So the answer is 24 meters. What do you notice?
That's our answer.
It's the same answer. These two answers right here are the same. So the obvious answer, 24 meters, and the area under the curve answer are the same, okay? And what I'm getting at here is the area under the curve of a velocity versus time graph will tell you your displacement, okay?
Yeah.
Which is kind of neat. So if you have a geometric situation on a velocity versus time graph, and you can sit there and calculate the area under the curve, it will tell you your displacement, your position at the end of that time interval. Okay? Okay. So if you need displacement of an object over a time interval, you can find the area under the curve geometrically, and this will tell you your displacement. It is not position. I think I just misspoke. This is not position. It is displacement. So if you started at 0, then it would be your final displacement, and that would add to whatever your position was, and so then it would be your position. But if you did not start at 0, then you would have to add your initial position to that to get your final position.
Oh.
Okay? So that's why I'm talking about here. There is a difference between position and displacement. This is just how much you moved from the beginning to the end. Okay? How far you went from where you started. It's not that you started at 0. It's not your final position. Okay? So make sure you understand the difference. So if this is the origin and I started here and I went through this displacement right here, this is my final position compared to the origin, but this is my displacement. Okay? And the area under the curve gives you the displacement. So make sure you understand that. Okay? And that is already the end of the section.
Oh. Well.
So that's pretty cool. We're done.